All right, let's look at some work on some inverse functions here. Let's check if this is working. Wonderful. So the idea about inverse functions is that everything has an inverse. Everything has an opposite. So the opposite of plus is minus, the opposite of multiply is divide, the plus minus above. So when we're talking about functions, the idea is that an inverse function that also exists. And so our functions are really defined as by passing the vertical line test. So a lot of different things are functions. So we have our parabola right there, and our parabola passes the vertical line test quite easily. Now, the idea that we can define an inverse, the inverse function or the opposite of the function is a function reflected over y equals x. So it's reflected over the diagonal. Now, this changes a lot of different things in regards to how we can define our function and how we can distinguish between a function and a relation, with a relation being something that's essentially not a function. So, a function's inverse is also a function if it passes a horizontal line test, and I'll do that in red over here. A horizontal line test. So this parabola above, it's going to fail the horizontal line test. So its inverse isn't a function, it's a relation. And that is because the inverse of a parabola is a sideways parabola like that, which, as you can see here, that function would fail the vertical line test. Or that graph would fail the vertical line test, so it's not a function. So it's about the idea of that reflection over the diagonal. And if you reflect this over the diagonal, you see that that they will have point of intersections, the graphs, on the line of y equals x, on that direct diagonal, which is really important. The other thing to make note of, like I've mentioned here, is that the domain of an inverse is the range of the original. On the other side of that, the range of an inverse is the domain of the original. So this is important because, one, if you find the domain and range of the original, it allows you to find the inverse a lot easier, and two, it's often a lot easier to find the domain and range of what you started with. Some of the inverses can get rather tricky. So let's just straight up start finding some inverses here. The way to find an inverse is actually more simple than you think. Change x to y, make y the subject. So if we have y equals x plus 1, swap x and y, make y the subject, minus 1 from both sides. That's the inverse of that function right there. Sometimes it ends up works pretty simply. And we see, if we were to plot these, now I can't bring up Desmos on my iPad, I probably could, but shuffling between things might. So if we just do a little graph here, 1, 2, 3, and we end up with x plus 1, which I will do in black. So this is the graph of y equals x plus 1. And then we have the graph of y equals x minus 1. We see that they are perfect reflections over the diagonal line of y equals x. You see, we reflected both lines over to each other, and it ends up working reasonably well. We're going to get into this a little bit more. The foundational aspect is being able to work with this in order to solve some problems. So let's go and solve a couple now that are going to be a little bit more difficult. Find the equations of the inverse relations of these functions. Now, another thing to make note is that if I take the inverse and sub it in, if I take the original and sub it into the inverse, I will get x. And if I take the original, substitute it into the inverse into the original, both of them work, I get x. That is because they will meet at the point of y equals x. So that point of y equals x is important for their intersection and how they relate to each other. So that will help you prove that your inverse is indeed a function and not a relation. But let's actually go through and solve a couple of these now. This element here will come into play a little bit later with some of our further questions, because what you can do, and a really important fact is that I'll quickly go back and take a look at, is we can actually restrict the domain of our inverses in order to make them functions. So let's take the parabola here. This is the parabola of y equals x squared. Now, it fails the horizontal line test, but let's say I was to restrict the domain. I'm going to restrict the domain so that, so that x is greater than or equal to 0. Now my function has an inverse. It passes the horizontal line test. It ends up having an inverse, and the inverse will be that one that I've just done right there, although not as well. It has an inverse. I could do the same on the other side. There it is right there. I could do the, oh God, that's quite grim. I could do the same from there as well. I can restrict the domain to x is less than or equal to 0, passes the horizontal line test. That function also has an inverse. So we can get creative with the domains of my functions, particularly my parabolas, in order to ensure that they have an inverse that is a function and not a relation. So let's go back to finding the equations of the inverse. Very important. Y equals x minus 2x. Let's find the inverse. We're going to swap x and y. We're going to make y the subject, divide both sides by -2. I've already subtracted 6. So I've got y equals x minus 6 over -2. Let's split this up. X over 2 plus 3. I can split my -2, so it becomes x over -2 minus 6 over -2. Negative make a positive. It becomes positive 3. That's my inverse. That's the equation of my inverse. We can do it again. Remember that f of x is the same as y equals. F of x just tells me that what I'm dealing with is a function. Let's swap x and y. Minus 2 from both sides, make y the subject. And the opposite of cubing is the cube root. Cube root of x minus 2. That's my function right there. You can see that it kind of works reasonably well. Now, I'm going to skip C only because we're going to do something very similar to C below, and I'm running out of space. Let's look at D. Find the inverse of this. Now, if I'm to find the inverse of this function, now I begin to make y the subject. Now, we reach an issue here. The opposite of squared is the square root, but it can be plus or minus the square root. That is because the square root of a negative is a positive number. So this right here, it's not actually going to have an inverse as it is, because if I was to substitute, this is the inverse here. Because I have plus or minus, and when I'm substituting that into the original, it's not going to end up working because it could be either option. So the inverse isn't a function. If I was to take the square root of x plus 9 or negative the square root of x plus 9, that would be a function, but we would have to define it. We would have to say, okay, we would have to restrict the domain, which it isn't asking us to do in this question, but we could do it in order to make the inverse a function, which can be important when we're graphing it. And you'll see how this manifests itself when we look at an exam-style question in a couple of pages below. So I didn't do C. We're going to do one like C right now. We've got a function right there. Explain why it's got an inverse function. Simply, we can say it passes the horizontal line test. Now, this type of function here is a fascinating looking hyperbola. It's going to have asymptotes, at 2 for the vertical, x equals 2, and the horizontal at 1. Now we could find those and we could plot them. I'm not actually going to be looking at that now. We're going to take a little bit further look into that later, but right now we're just looking at what we've been asked. Passes the horizontal line test. You know what? Let me quickly see if I can graph it super fast and just kind of filibuster for a little bit. And hopefully I'm able to work out a way to quickly get a graph onto that. Like I said, it's got an asymptote at x equals 2, and if we look at the y asymptote, it's 1. Now remember how we find the y asymptote? We divide each term by the highest power of x. I believe we did do this in class. X over x minus 2 over x, that becomes 1, and anything divided by x goes to 0. So it's going to have asymptote at 1, 2. This is an appalling graph, and it's going to look something like this. We're not super concerned with what we've got. That passes the horizontal line test. The inverse will be a function. Thankfully, we don't have to draw it because it is going to be a little bit of a pain. But what we can do is utilize this in C, this beautiful image I've drawn. Find the equation of the inverse. Let's swap x and y. So we have y equals x plus 1 over x minus 2. Let's simply swap these. I need to make y the subject. We're going to do a bit of manipulation in my equation. So let's multiply both sides by y minus 2. Because y plus 1. Now, I'm going to expand here. Now, the reason I'm going to do this is so I can collect my y terms together on the same side. So we're going to have xy minus y equals 1 plus 2x. So I've minused y from both sides, and I've added 2x to both sides. I'm going to factor out a y out of the left-hand side here. Now, you'll notice, even though these techniques often seem a little bit obscure, once you've done it once, you're going to be able to do it again and again. You're going to be able to do it repeatedly. So you'll see something and be like, that's weird, but you'll recognize that you'll be able to do this again and again, particularly with these types of problems. Divide both sides by x minus 1. And there we have it. That's the equation of my inverse, done. Write the domain and range of the inverse function. Let's go back to my original here. My original, which I drew a graph of right there, the domain of that, you can see, is all real x, except x equals 2, the asymptote. And the range is all real y, except y equals 1. So for my inverse, which I'll do, maybe I'll do it in a different color. So my inverse, the domain of this inverse is all real x, except x equals 1, which is the range of the original. And the range is all real y, except y equals 2, which is the domain of the original. And you're going to get a bit of practice at this kind of thing as well. Now, this all kind of leads to the types of questions we generally get asked. This is a 2018 HSC question. So it's worth 2, 1, and 3. It's worth 6 marks in total. And we're going to take a look at answering this question in order to get these 6 marks. The first one. Consider the function. We got the diagram of x over x squared plus 1. A terrible function. It is just whatever this is. It's just ridiculous. This is what it is. We're considering the function for x is greater than or equal to 1. It's important we're reading and checking out everything. State the domain and range of the inverse. Best part about this, we know that the domain of the... So let's look at the original, because the domain of the original is the range of the inverse, and the range of the inverse is the domain of the original. So for the original, the domain, it's x is greater than or equal to 1. We're just looking at the function from this point onwards there. That's all we're looking at. Just that area there, that region there. I'm just going to get rid of that so we... There we go. Oh, another dot, I think, yep. So that's the original. The range of the original, we can see here it's a half, and it's going down. It's going down to the axis, but we get the feeling it's not going to cross these axes. We could check by looking at the asymptote. So let's quickly look at the asymptote. Divide each term by the highest power of x. We know that's going to be 0, that'll be 1, that'll be 0. So it's going to be 0 over 1, which is 0. Now, knowing that we can pass horizontal asymptotes, this particular method here checks for asymptotes at infinity and negative infinity. So it checks it at the extremes. When we're looking close to the axes, we often need to examine what is happening as my graph approaches 0. We can do that with a quick sketch, or if the sketch is already given like this. We can particularly tell if we're looking at an even or an odd function, and we'll notice that this function here is odd, and that can help us determine a lot of odd functions are going to pass through a horizontal asymptote. So the range, we can see here, it's going to be between a half. Oh, that's not how you write a half. It's between a half and 0, and it's equal to a half. Very important, it is not equal to 0. It's between 0, but it could be a half. 1 mark each, working like that. So the domain and range of the inverse, the domain of the inverse is 0, is greater than x, is less than or equal to a half, and the range of the inverse is just y is greater than or equal to 1. Really, really, really works quite well. Super simple. And we can particularly use this for part 2. We got to graph this. My graph's going to be beautiful and quite poor. So the best part about this is that the x and y values of the inverse swap. So x and y of inverse are opposite x and y of original. I'm just going to write OG, which means that this point I'm looking at right there, the point I've just circled that I'm now erasing, that point on my inverse is not going to be 1/2. It's going to be a half 1, which is going to be right there. The x and y coordinates have swapped. We can look at the domain and range of the inverse. We know that y is greater than or equal to 1, which is on here, and x is between 0 and a half. So it's going to end up going just like that. It's going to be a little bit, because you can see the shape of the previous graph, it's kind of going to be going around and then in a little bit, just like that. Knowing also that it is a reflection over y equals x, you can use that diagonal reflection to help you if required. So that's the domain and range. That's a graph of the inverse. 3 marks already. Last year, to get a E4 in the final exam was 32 out of 70. That's it. An E3 was 32 out of 70. So we're looking to push ourselves far beyond that into the realm of the 50 out of 70 for the E4. Like LeBron, we strive for greatness. And then part 3, find an expression for the inverse. Let's do it right now. Y equals x over x squared plus 1. Swap x and y. This is where I talk about some of those techniques we may have never seen that are going to become quite useful. Going to have to times both sides by y squared plus 1. So I have x, y squared plus 1 equals y. I'm going to do something strange here. I'm going to expand. The idea is I want to get my y's on one side and my x's like on one side as well. So we have x, y squared minus y plus x is equal to 0. The most insane thing about this, other than the fact that I can't add a new page, so I'm really going to run out of room. This is actually a quadratic if you think about it. Y squared, y constant term. We can factorize that. We can factorize that with the quadratic formula relating to y. Normally we write x equals, but because x squared is no longer the subject, let's just look at it as y equals negative b plus or minus the square root b squared minus 4ac over 2a. b here, a is x. We can have you can have variables as your coefficients and your terms. That's not out of the ordinary at all. b, -1. c is also x. Let's do it right now. Negative b, so -1, plus or minus the square root of -1 squared minus 4 times x over 2a, which is going to be 2x. So we have y equals 1 plus or minus the square root of 1 minus 4x squared over 2x. That may not look like an answer, but it is. We can even go a little bit further. Let's just quickly go back to the domain and range of my inverse. We know that y has to be greater than or equal to 1 from my inverse. If I was to this, which means it's only going to be plus 1 minus 4x squared over 2x. And that is because if we were to subtract it, there's a chance it could be less than 1. And it will be less than 1 because 1 minus anything, like that right there is my anything. 1 minus anything is going to be less than 1. And 1 divided by 2 times something, it's already less than 1. We can't have this. So that ends up being the inverse of what we are looking at. Now, this is a giant crash course in inverse functions. This is part 2 of the work on further functions, and part 1 will come up a little bit later.